Hi everybody, in this video we will talk about many things. The first thing we will talk about is pressure, or more specifically, partial pressures. We all know what pressure is. Pressure is the force over a certain area. If you have a sample of gas, it will exert a certain pressure on the container because the molecules are constantly moving and bumping into the container. Now, if you have a sample made up of multiple gases, such as one that's made out of yellow gas and green gas, then each gas will have its own pressure. And the pressure that each gas has is called a partial pressure because it is a part of the entire pressure. So Dalton's law of partial pressures states that the total pressure is equal to the sum of the partial pressures of the gases that make up the sample. So you could have 3, you could have even more if you need it, or you could just have 2 gases. And this ... just says that you could have as many different gases as you want, but in the end, the partial pressures for each individual gas that makes up the sample has to add up to the total pressure. So in the example below, the pressure or the partial pressure of the yellow gas plus the partial pressure of the green gas is equal to the total pressure in the container, also known as the pressure of all the gases combined. Now let's move on to our second topic. If we collect a sample of gas over water, such as here where we're collecting hydrogen gas above water through maybe some sort of reaction that brings up the H2 gas, then the gas over here is not just made of the H2 gas that goes in, it's also made of many water vapor molecules that evaporated from the water that you're collecting the gas in. And the reason why there's water vapor is because of evaporation. As you know, if you put a cup of water outside in the hot sun, your water will evaporate even though it's not at its boiling point. And this occurs because no matter what temperature it is, as long as water is water, it will like to evaporate. Note that most substances, such as liquids or even solids, tend to be able to evaporate to a certain extent. Some things, like water, don't like to evaporate as much as other things do. For example, acetone likes to evaporate really quickly as a liquid, even though it's not at its boiling point. And these substances that really like to evaporate and turn into a gas very quickly are called volatile substances. And water is not really considered a volatile substance since it doesn't tend to turn into a gas very quickly, unlike many other things like acetone. So in the water sample here, the water evaporates a little, and that's why there are small amounts of water vapor inside this gas sample. And when a liquid or a solid evaporates, it creates something called a vapor pressure. And a vapor pressure is the pressure exerted by the vapor of the gaseous form of whatever liquid or solid you have. So for example, the water is evaporating and creating a vapor pressure that is made up of water. So in this table over here, I compiled a list of the water vapor pressures at different temperatures. So as you notice, at higher temperatures, the water vapor pressure increases. And this is because at higher temperatures, the water molecules are moving faster, and they tend to like to go into the gaseous state since they have more energy at higher temperatures, and that's why they have a higher tendency to evaporate and turn into a gas. Now, what do these vapor pressures mean? Well, if you have a closed container and you have a certain amount of water, the water will evaporate until it reaches the vapor pressure that it wants. So for example, if this container was kept at, let's say, 25 degrees Celsius, then the water will want to keep on evaporating until it reaches a partial pressure of 23.8 millimeters of mercury. And once it reaches 23.8 millimeters of mercury, then evaporation will stop and the system will reach equilibrium, which means that it won't want to evaporate anymore. And that's what's special about vapor pressures. At a certain temperature, the water vapor pressure that it aims to achieve in a closed container is always constant. So, for example, at 40 degrees Celsius, the water will want to achieve a water vapor pressure of 55.3 millimeters of mercury in order for it to reach equilibrium. So let's get back to the previous slide. Gases that are collected over water are called wet gases because the gas is contaminated with water vapor, and that's why it's called a wet gas. Now, before I move on to the next topic, let's review how pressure works. We can think of gas pressure as the combination of how fast the particles move, which is directly correlated to the temperature. And remember, temperature is the average kinetic energy, and kinetic energy is responsible for the movement of particles. And gas pressure is also dependent on how dense the environment is, and the density of the environment is dependent on the number of moles of substance inside the container, as well as the volume of the container. So let me look at this picture here. In this picture, we have a sample, and in the red arrow, you see that the temperature is increased. And when the temperature is increased, particles will move faster. And when particles move faster, they exert more force on the container than usual. And because there's more force, then the pressure increases. Now let's look at the second situation, where instead we decrease the volume. Now, decreasing the volume increases the compactness of the environment, and by making the environment more compact, molecules will crash into each other and the container more often, and because there are more frequent collisions on a certain area, then the pressure will increase since there's technically more force going on at a certain time because of how compact the environment is, since the particles are crashing into the container more often. So therefore, decreasing the volume increases the pressure. Now let's take a look at one last scenario, where instead of doing this or this, we can increase the number of moles in the container, and this causes the environment to be more compact. And since it's more compact, particles bump into the container more often, and as a result, they exert more force at once because they're crashing into the containers more frequently at once, and this increases the pressure. So this is just a review of the relationship between P, V, N, and T. Now let's remind ourselves that at a certain temperature, there is a corresponding vapor pressure that it wants to achieve in order to maintain equilibrium. In other words, at a certain temperature, a certain equilibrium water vapor pressure will be present. So let's take a look at a situation where we have water at the bottom of the closed container and there's a movable piston. So we're assuming that the temperature is kept constant, but let's not assume anymore. Now let's do something cool. Let's actually move this piston up and increase the volume. So if we increase the volume of the container, what do you think will happen to the pressure at first? Well, at first, there is a certain amount of water molecules, and when you suddenly just move up the piston, those water molecules will spread out. And when they spread out, you can assume that the moles is also constant at that point. And since T and N are constant, then if you increase V, then the pressure will suddenly drop when you increase the volume. So the system is like, wait a second, the pressure is now decreased. And remember, initially, this system was at equilibrium because the water vapor exerted enough of a vapor pressure to maintain the equilibrium vapor pressure that it wanted. So let's just say for practicality that this system was at 25 degrees Celsius and it had a water vapor pressure of 23.8 mmHg. So let's just say that this sample had the vapor pressure that it wanted at equilibrium. And now that you increase the volume and you thus decrease the pressure, the new pressure of the water vapor is not the pressure it wants. This was once 23.8, right? I think it's, yeah, okay, I'm right. And now the pressure is less than 23.8. So what do you think the system will do to maintain equilibrium? So at first you're like, well, can you increase the temperature? Well, the system doesn't have that type of power. The system can't just increase the temperature without help from anything. It has to rely on what it has. And then what it does have is these excess liquid water molecules that can evaporate at any point. And for this reason, if the system wants to keep the pressure it wants, aka the vapor pressure that it wants according to the table, then it must evaporate more. So this water will, as a result, evaporate a little more to add more water vapor, and it'll add enough, just enough so that the pressure goes back up, and as a result, the equilibrium pressure is achieved. So this system reacts to the increase in volume by releasing more water molecules into the container so that it can reach the equilibrium pressure once again. And let's take a look at equilibrium and how it works. So the equilibrium exists between liquid water and gaseous water. At equilibrium, nothing happens because the rate that the liquid turns into a gas and the gas turned into a liquid is the same. So if they're the same, then they cancel out and thus nothing happens. And we can see it here because nothing's happening there. But when you're not at equilibrium, one of the rates is higher than the other. So the rate at which the liquid turns into a gas is called the rate of evaporation or vaporization, and the rate that the gas turns back into a liquid is called the rate of condensation. So when these two rates are equal, also known as when these two arrows are the same length, then the rates are equal and they cancel each other out, so nothing happens. But what happens if you want the water to evaporate overall? Well, if the water needs to evaporate, then the rate of evaporation, which is indicated by the forward arrow, has to be a lot larger than the rate of condensation. And if you add these two arrows together, you'll get a net, evaporation of the water. And this shows that when you're not at equilibrium, the system wants to evaporate more than it condenses, so that overall the net result is a net evaporation. And that's exactly what's happening here. The system not at equilibrium wanted this pressure, and it wanted the pressure, so it decided to increase the rate of evaporation, and that rate of evaporation overcame the rate of condensation, and as a result, the liquid turned into a gas more quickly than the gas turned into liquid, and thus the overall system decided to turn the liquid into a gas. Now, this type of equilibrium, where two things are happening at once and one cancels out the other or one overcomes the other, is called dynamic equilibrium. And the reason why it's called dynamic is because it's constantly changing, but when you add it up together, nothing happens. And that's what dynamic equilibrium means, because things are happening, but overall, nothing is happening. We will get more into equilibrium in the future, but this is just a great introduction to the idea of equilibrium in a container. Now let's go on to another topic. What happens if you leave an open container of water out for it to evaporate? Now we all know that the water will evaporate and you'll have no water left. But why does that happen? Well, what happens is that the outside or the atmosphere outside us has a water vapor pressure that is less than the ideal vapor pressure that it wants according to the table that we wrote. So the system wants to achieve this water vapor pressure and make it ideal and thus reach equilibrium. So the system will keep on evaporating, but then the system realizes that the volume is way too large. Like our atmosphere has, according to the internet, around 1.4 billion cubic kilometers worth of volume. So no matter how hard this water tries to evaporate to achieve the equilibrium water vapor pressure, it will never achieve it because the amount of water in here is too small to make a difference in the gigantic volume that our atmosphere takes up. And thus, as a result, all the water evaporates and the system will never achieve equilibrium. So that's why our water evaporates, and that's a cool lesson relating to equilibrium. Now let's go back to PV equals nRT, because I want to introduce a new concept. So in order to introduce this, I want to make P and N our variables while keeping V, R, and T constant. So we have to move the variables to the left and the constants to the right. Now I did this in the previous video, so feel free to watch that if you want to know why I'm doing this. So I will move P over here, and I'll divide both sides by N to cancel out the N on the right, and I'll divide both sides by V to cancel out the V on the left, and you get P over N equals RT over V. And RT over V are all constants, so I could call that a K, and thus I derive the relationship that P1 over N1 equals P2 over N2. Now I can change this even further and switch these two because it's algebraically allowed, and say that P1 over P2 is equal to N1 over N2. So let me change things up just a little bit. Let's, instead of labeling 1 and 2, let's say that the pressure down here is the total pressure, and let's just say that this is the total number of moles. And if the pressure on top is the partial pressure of gas A, then the moles here will be the moles of A. So notice how we derived this, and now let's move one step further. If we multiply both sides by the total pressure, we get that the partial pressure for gas A is equal to the total pressure times the mole fraction for gas A. The mole fraction is another way of saying the moles of A over the total moles. So in this case, the mole fraction for A is the moles of A over all the moles. And thus we derived this formula, which will be very important in the future when we do math. Let's take a look at this example. If a student collects 152 milliliters of gas over water at 25 degrees Celsius and finds that the pressure inside the container is 758 millimeters of mercury, then what is the partial pressure for the H2 gas, and what is the number of moles of H2 gas? So these are the two things we are trying to find. Now this is a type of question known as the wet gas problem, and the reason being is that this gas right here has not only H2 gas, but it also has some water vapor in it because there's a water vapor pressure that the water is trying to achieve. So this pressure is equal to the pressure of H2 and the partial pressure of the water vapor. Now, we could find the partial pressure of the water vapor by looking at our table, which shows us the different vapor pressures for water at different temperatures. So at 25 degrees Celsius, it seems like the pressure of the water is going to be 23.8 millimeters of mercury. So let's use that to our advantage. So I think I skipped a slide too far. Oh, there you go. So we know that 758 is equal to the pressure of H2 plus the partial pressure of H2O, which is 23.8. Now, subtracting 23.8 from both sides, you get the pressure of H2 to be equal to, 734 millimeters of mercury, and that is the answer for the first part of the question. Now, if we convert 734 millimeters of mercury into atms, then we get 0.966 atms, because if you remember the conversion factor, that 760 millimeters of mercury is equal to 1 atm exactly, and all I did was I divided this by 760 to get 0.966. So let's now use PV equals nRT to find the moles of H2. So on the next slide, we will write the formula. So PV equals nRT. Now P this time will be for just the H2 gas, and the partial pressure of the H2 gas was found to be 0.966 atms. Remember how we have to use atms in the ideal gas law? Because the R constant that we use is based on the fact that this unit here is in atms, this in liters, this in moles, and this in Kelvin. So don't forget to convert all your pressures to atms before doing the question. So our volume, well, the volume of H2 gas is just the volume of this container, and the volume of the container is 152 milliliters. Now, 152 milliliters is also 0.152 liters if you convert from milliliters to liters. But a good way I like to do it is I like to move the decimal place 3 times to the left to convert to liters from milliliters, and it always works. So this is 0.152 liters. Let's not write the units, is equal to N. Now this is the moles of H2 times R, which is always 0.0821, and our T is 25 degrees Celsius, but we have to convert to Kelvin, so we have to add 273.15, and we get 298 Kelvin, so this will be 298, and doing the math, you get that the moles of H2 gas, the moles of H2 gas present is 0.00600 moles of H2 gas, and that is the answer to the second part of the question. Now we can do this question using mole fractions, which is the thing we just learned over here, where X is the mole fraction for a gas such as gas A. So let's start off this problem by finding the total number of moles of gas. So the total number of moles of gas can be found using PV equals nRT, but this time we're looking at the total. So the total pressure was found to be 758 millimeters of mercury. Now we can't plug that in, we need to change this. So 758 millimeters of mercury divided by 760 will give us 0.997 atmospheric pressures. And note that you should use a calculator to do that, or else you would be wasting a lot of time. So our P is 0.997, and our volume is just the volume of the container, which is 0.152 liters once again. And this is equal to the moles of total times R, 0.0821, and our temperature again is the same, so 298. And by doing the math, we get that there are a total of 0.00620 moles of gases, which includes both the H2 gas that we are collecting, as well as the H2O gas that is forming because it wants to achieve the water vapor pressure at that certain temperature, since this is a wet gas. So now we want to find the moles of H2. So if we multiply the total moles times the mole fraction for H2, we will get the moles of H2. And this is because this fraction tells us out of the entire amount of moles, only a certain fraction of it is H2. So by multiplying the total by the fraction of it that's H2, we get the moles of H2. And let me show you how that works. So how do we find the mole fraction? Well, remember that the partial pressure for H2 is equal to the mole fraction for H2 times the total pressure. So this was derived right there, and we're just using it right now. So the partial pressure for H2 was calculated to be 734 millimeters of mercury, or 0.966 atms. So let's use 0.966 atms for simplicity, since if you're not sure whether to use torr or millimeters of mercury or atms, I highly recommend you just go by atms, just for simplicity. Although for this case, you could use any type of pressure as long as the units are the same. So 0.966 atms is equal to the mole fraction for H2 times the total pressure, which was found to be 0.997 atms. Now, dividing both sides by 0.997, you get the mole fraction for H2 is equal to 0.968. So now that we know the mole fraction for H2, we can use this in order to find the moles of H2. So the overall moles is 0.00620, and we have to multiply that by the mole fraction for H2, which is 0.968, and we will get the moles of H2, and this turns out to be 0.00600 moles of H2. Notice how the answer matches the both ways we do